Hello and welcome to lesson 4. Today's lesson is called Boyles Law, and that's what we're going to be looking at in today's lesson. It's the first of 3 lessons on gases, and we're going to look at 3 separate relationships in 3 separate lessons, each of which will be relatively short lessons, and then in lesson 4 we'll pull all the ideas together into one one gas law called the ideal gas law. And then finally, in the next couple of lessons afterwards, we will look at some more mathematical modelling of gases. So the first thing I want you to do in today's lesson is to pause the video and think about these 3 questions. So the answer to these 3 questions, it depends. It depends on what you keep constant. It depends on the exact situation. So what I suggest you do is to open this simulation here. So you can either type this link in, or I'll put it in the Google Classroom, or if you just type in PhET gas simulation, you'll get it. And I want you to play around with the simulation for a little bit. I want you to try varying the pressure, the temperature, etc. And again, see what happens in relation to these 3 questions. So pause the video now and play with that simulation. Okay, welcome back. So hopefully you learned something. A lot of what we're doing is an extension of GCSE, and a lot of it is kind of obvious in some ways, but we're going to hopefully extend your knowledge today. So what is Boyle's Law? So Boyle's Law is the relationship between pressure and volume in a gas. So it follows this relationship here. It's a curve, and more specifically, it's inversely proportional. So in simple terms, as volume increases, pressure decreases, but mathematically it's an inverse relationship, or inverse proportional relationship, which we'll look at on the next slide. Now, importantly, as with any scientific test or experiment, we've got our variable and everything else is constant. So here, what has to be kept constant? Well, obviously the temperature has to be kept constant. Also the mass of gas as well. So the volume can change, but the mass contained in whatever container you've got must be the same. So another condition is obviously it must be a kind of inside a container, or we might say it's a closed system. No matter, no mass can add or be subtracted from this system. So think about this question here. How can we actually achieve a constant temperature in the real world if we're changing the volume or the pressure? So it's hard, but you can do it. You basically just have to make sure the change happens slowly. If you increase the pressure a little bit, the volume will decrease. And then if you wait a minute, 2 minutes, 10 minutes, however long, any heat that's built up in the system will dissipate through the container to the surroundings, and it will remain at the same temperature. You can then increase the pressure again, decreasing the volume, and it will heat up a little bit. But if you only make small changes and you wait, again, that temperature will equalize. So it's a constant temperature, but we have to do these changes slowly. So mathematically, we said it's an inversely proportional relationship, which means that pressure is proportional to 1 over volume, or pressure equals some constant divided by volume, or pressure times volume is a constant. So if you plot that on a graph, it looks like a curve. Importantly, as you'll know, these will never reach the axes. They will just get closer and closer. We never quite reach it. If you plot pressure against 1 over volume, you get a nice straight line like this, or equally volume against 1 over pressure, you get a nice straight line. Also, sometimes you might see pressure times volume plotted against either volume or pressure. But just think to yourself what that graph would look like. So pressure times volume is a constant for every single pressure and every single volume. So if you plotted pressure times volume against pressure, for example, it's just a constant. It'd just be a straight line like this on the graph. Okay, have a look at this graph here and think about what am I changing as I go from this line here to this line to the very top line. So if you start at a fixed pressure and you start to increase the volume, or how have you managed to increase that volume? Hopefully you've realized you increase the temperature. Likewise, if you have a fixed volume, but you increase the pressure, you are also going to increase the volume. If you want to see this visualized, and I'd recommend that you do to really get this clear in your mind why this is the case, go back onto that FET simulation, the link I showed you earlier, and you'll be able to model this using the simulation. It's worth doing. So this is the lowest temperature, this is the highest temperature. The red lines themselves are lines of constant temperature, as we explained. And another word for this is isotherm, or isotherms. So isothermal means the same temperature. Iso generally means the same. Thermal is relating to heat temperature. So isotherms are these red lines. All right, question for you to try. So pause the video now and try this question. Okay, welcome back. So it's a relatively straightforward question. So it tells you a hand pump of this volume is used to force air through a valve into a container of this volume, which contains air at initial pressure of this. Calculate the pressure of the air in the container after one stroke of the pump, assuming the temperature is unchanged. So we obviously need to recall that pressure times volume is a constant. So the initial pressure times the initial volume is the final pressure times the final volume. Now, I meant to put these I's and F's as subscripts, but I made a mistake. Usually we would write them as little i's at the bottom. But the initial pressure times the initial volume is going to be 6 times 10 to the minus 4 meters cubed times by 101 kilopascals. The final pressure is what we're trying to work out. And the final volume, well, this pump here has been compressed in order to force the air into this volume. So the final volume is 4 times 10 to the minus 4 meters cubed. So now it's just a case of plugging all those numbers into the equation, and you should end up with 150 kilopascals. So you might be wondering, do I need to change my units from kilopascals to pascals? You can if you want, but actually you don't need to. So if you think about what this equation actually represents, it's just a ratio here. We've got a pressure here, and then we're also going to divide by this final pressure. So pressure over a pressure, it doesn't matter whether it's in kilopascals, megapascals, pascals, micropascals, that's going to cancel out. So in actual fact, we don't. Similarly, it doesn't actually matter what units our volume is in. It could be liters, it could be milliliters, centimeters cubed, etc., because it's just a simple ratio. In this case, we don't actually need to change the units. All right, so another question for you to try. Pause the video now and think about this question. I will just say that these were taken on an aeroplane for my latest holiday. Okay, so should be fairly obvious. When I was on the runway before we took off, my crisps looked like this. As I flew up really high in the sky, my crisps look like the left-hand picture here. So the volume has increased because the pressure in the aeroplane has decreased. Now, it doesn't decrease entirely, obviously, because we would die up there. But the pressure does decrease a little bit relative to the pressure on the ground, which is also why your ears pop, because of the differences in pressure inside and outside your ears. When they pop, that's the equalization of the pressures, because obviously we never really want, nature never wants there to be a pressure difference. It's always trying to equal out the pressure. And ideally, nature always wants things to go from a high pressure to a low pressure. Air pressure always pushes from a high pressure to a low pressure, which is useful when we're explaining a lot of phenomenon. All right, another question, slightly different this time, but this is a graph of water boiling temperature in degrees Celsius versus pressure. Okay, so what is happening to the boiling temperature of water as we change the pressure, and why? So it should be fairly obvious that obviously as we increase the pressure, the boiling temperature is increasing. I don't know exactly what mathematical relationship this follows, but it doesn't particularly matter. What's important is that it increases. Why is that? Well, the higher the absolute pressure it is, and that just means the pressure outside the water, the more gas particles from the air are bombarding the water surface at a given moment. So what are they doing? They're basically hitting any water molecules that are trying to evaporate from the surface and forcing them to stay back down, essentially. So as we increase the pressure, there's a kind of more force almost keeping the water molecules down on the surface, which means we actually need to increase the temperature of the water, so we increase the energy of the individual water molecules enough for them to overcome that higher pressure. Only once they've got enough energy can they actually be moving fast enough and with enough force to leave the surface and essentially be kind of equal in energy to the higher pressure gas molecules. Equally, if we decrease the pressure, so if we take a can of water up a mountain, Mount Everest, for example, and we decrease the pressure, the water will boil at a lower temperature. And I think at the top of Mount Everest, it boils at like 70 degrees or something. I'm trying to remember to post a link to a really good video on this in the Google Classroom, so you can see this. What this also means is if you go into space, where there is zero pressure, then the temperature of the water boils can be very, very low, which is interesting. Okay, part 2 of Thurston is looking at verifying Boyle's law experimentally. So obviously this is something we'll do in class when we return. So we won't spend too much time on it now, but it's useful for you to see it. So there's 2 methods that are commonly used, one on the left and the one on the right. Pause the video now and think about how you would test the idea that pressure is inversely proportional to volume for both the left one, which is pretty easy, and the right one, which is harder. And I'd strongly recommend you really do give writing a method for this right-hand one a go, because there's a couple of little tricks in it that are really worth thinking through, because these are exactly the kind of tricks that they might try and catch you out with in an exam. So pause the video now and write a method. Okay, welcome back. So the left-hand one is really easy. You typically have a container here with air in. So this is our starting volume of air. It doesn't really matter what the units are, just for the purposes of a general method, but we're probably going to be working in centimeters cubed. We have some oil here. It's typically dyed red, so you can see it. A pressure gauge to record the volume, and then we use a foot pump usually. So you pump in air. That's going to increase the height of the oil and decrease the volume as we increase the pressure. So obviously it's just a case of recording various pressures against various volumes, plotting a graph, and then plotting pressure against 1 over volume, seeing if it's a straight line through the origin. Importantly, and hopefully you remember this from what I was saying before, when we take a measurement, we need to wait for a minute or 2 to make sure the temperature has settled, make sure any heat that's built up when we pressurize the system is dissipated through the glass tube. As long as we do it slowly, we will get a pretty good set of results. If we do it quickly, then we may find it heats up and the pressure is a little bit higher than it should be because of that extra heat. The method on the right is a little bit trickier because we're sort of doing the opposite here. We've got a syringe full of air and we're adding masses onto this syringe. So the more masses we add, the higher the volume is going to be here. So initially when you do this, it's very easy to think, hang on, I'm increasing the pressure by putting on masses and I'm increasing the volume. That's complete nonsense, isn't it, sir? Well, there's a little trick here. Okay. Why doesn't the when you put a mass on, why doesn't this plunger just fall out completely? Well, the reason it doesn't fall out completely is because the air around it is pushing it back up. So standard atmospheric pressure, which is about 100,000 pascal, sorry, 100,000 kilopascals. Sorry, completely wrong. 100 kilopascals or 100,000 pascals. That is pushing it back up. So when we add masses on, we are actually decreasing the pressure inside. Okay. So if you could imagine that the pressure we put going down was equal to the pressure outside, in that case, then we could pull that plunger out completely. Or if the pressure added was greater than the atmospheric pressure, then we'd pull it out completely. However, if it's less than that, then we're decreasing the pressure on the air inside because we're trying to pull against the air around it. You might, if you're like me, when I first saw this, need to think through this a couple of times. But once you get it, it will make complete sense. So what are we doing here? Well, we're going to add masses on. Each time we add masses on, we're going to record the volume on the syringe. And we're going to repeat that for 10 or so times, again, making sure we do it slowly. Now, we need to be very careful what we plot here. We're going to plot atmospheric pressure minus the pressure that we've applied from the masses. And what is that pressure? Well, it's the force done by mass times gravity over the area of the syringe. So we can actually work out what the pressure is, because pressure is, of course, force per unit area. So working out the force is easy, mass times gravity. How are we going to work out the area of a syringe? Hopefully, you thought vernier calipers are sensible to use. You'd obviously need to measure the internal diameter of the syringe using some vernier calipers. There's one more subtlety here. What is our starting volume going to be for the syringe? A lot of people, when they do this, they have the starting volume at 0 because they think obviously you're going to start at 0, but that won't get you anywhere, because if the starting volume is 0, then there's no gas in there to actually expand, and you won't have any meaningful results. You need to start the syringe at, I don't know, 4 milliliters, 5 milliliters, something like that. So there is some gas in there, and then when you add the masses on, we can actually expand that volume of gas. If you start with nothing, it's effectively a vacuum, and it's almost impossible to pull the plunger down, because the strength, effectively, of the air pressure, was slightly bad terminology, is incredibly strong. 100,000 kilopascals. Sorry, 100 kilopascals is 100,000 pascals, which is 100,000 kilograms per meter cubed. I, for one, cannot lift 100,000 kilograms. And I know this is only a small fraction of it, but it is still a lot of force, effectively, that's needed. So here is a full method. You can pause the video and read through this. It will, of course, be useful when we come back to school. And here is another note about the calculating pressure. I was talking about subtracting it from atmospheric pressure. So again, you can pause the video read through this, make sure you're happy with it. So what you're going to do now, you're going to complete the Google form quiz for this lesson. And I also would like you to find out what these words mean. So find out definitions for these words. They are all very important. I'll see you next lesson. Goodbye.